Hello everyone, welcome to my 10th grade math classes. We are in first chapter real numbers, and in this video we are revisiting rational numbers and their decimal expansions, and then lead to from that theorem 1.5 and 1.6, right? Okay. As we studied earlier in 9th grade, already you have studied in your 9th grade that rational numbers of the form p by q are either terminating or non-terminating. Terminating or terminating decimal expansions, all p by q forms are either terminating decimal expansions or non-terminating and recurring or repeating, non-terminating and repeating decimals, right? Okay, here now we are going to consider and explore when exactly this p by q form will be a terminating or when it can be exactly non-terminating or repeating recurring decimals. Okay, so now let us consider this with some examples, right? Let us start taking examples. Let us take 0 point, for example, 625. This can be written as 625 by 1000, right? And also we can write it as 625 by 10 cube. We can write it as 10 cube. Similarly, let us take another example. I'll explain all this why I am taking these examples. Next, I can write it as 56 by 1000, which also can be written as 56 by 10 cube again. And we can also write one more example, 0.0175 will take, so that we'll get the denominator as 175 numerator, denominator as 1 after 4 zeros. As we have 4 digits after the decimal, we're having 10,000 in the denominator, which can be written as in the exponential form 10 power 4. Okay, sometimes we can take the example like 12 point, not always 0 point. We can also take 12.572, which we can write as 12,572 as numerator, and the denominator, as we have 3 digits after the decimal, we can write it as 1000, and also we can write in the exponential form like this, the denominator as 10 cube, right? So as you know, every decimal number like this, every decimal number can be expressed as the denominator as fractions with denominators 10 cube or like powers of 10, always 10, 10 square, 10 cube, etc. All the decimal expansion numbers can be written in the form of fraction form where the denominator is of powers of tens, right? And now let us further cancel the common factors from each and write them each in the form of simplest form, right? So let us do the cancellation. 625 by 1000 can be written as I can write 625 in the form of 5 into 5 into 5 into 5 by 10 cube. This 10 cube also I'll put in the form of 2 cube into 5 cube, as 2 cube into 5 cube is also same as 2 into 5 whole cube, which is 10 cube, right? Okay, in this 5 cube can be cancelled with 5 3s, 3 5s, and you are left with 5 by 8 finally. Or you can also write as 5 by 2 cube only. Okay, next this 56 can be written as 7 into 8 by 2 cube into 5 cube. This 8 also I can write as 2 cube, actually 2 cube is also 8. So this 2 cube and 8 are same. So I can write it as 7 by 5 cube, right? And observe this 175. This 175 I can write as 5 into 5, 5 into 5, 25 times 7. 25 times 7 is 175, and 10 power 4 I'll write as 2 power 4 into 5 power 4, right? And from this I will cancel 2 5s from this to 5 power 4. I'll write it as 2 here, 5 square now. So 7 by 2 power 4 into 5 square, right? Next, this number also. This 12,572 can be factorized like prime factorization, and I will write it as 2 into 2 into 7 into finally 449, which is a prime number. You can leave like that. By 10 cube, I'll write as 2 cube into 5 cube. Okay, from this 2 cube, 2 2's you can cancel from 2 cube. So 1 2 will be left down. So you are left with 7 into 449 by 2 into 5 cube, right? So now you observe all the patterns of the answers what you got here. What did we do? We converted a rational number of the form p by q into the form of a by b, which is in a simplest form, where a and b are co-primes here. 5 and 8 are co-primes. They don't come in any more same table, so they are called co-primes, or it is in simplest form. So we converted a rational number into simplest form. So this simplest form, all the denominators you try to understand here. This is 2 cube and this is 5 cube, and here this is 2 power some number, 2 power 4 and 5 power 2, and here this is also 2 power 1 and 5 power 3. So every denominator, you observe all the denominators of these examples, they are all either powers of 2 or powers of 5 or either both. You may observe the denominators may contain either 2's and 5's, or only 2's or only 5's. So every terminating decimal, you can understand that they will have a denominator of all powers of 2 or 5's or both. So you can also check with some more examples, and you also can conclude that these all examples, that any real numbers which has a decimal expansion, okay, decimal expansion which is a terminating, these are all terminating, they all can be expressed as a denominators with powers of 10, with the powers of 10 in the beginning, and lead to powers of 2's or 5's or both. So a rational number of the form p by q, where q is of the form 2 power n into 5 power m. The rational number in the form of p by q, where p can be anything, q can be the denominator which is in a decimal expansion. If you write in a prime factorization form, it can be in the form of 2 power n and 5 power m. Q is of the form, denominator will be always of the form 2 power n into 5 power m, where m and n are any non-negative integers. So any terminating decimal can be expressed in the form of p by q, where the denominator is of the form, denominator compulsory, the denominator will be, if it is a terminating decimal, it will be of the form 2 power n into 5 power m, where m and n are any integers. Only 2's means it will have 5 m plus 0, so there will be no 5 at all. So only 2 powers will be there. Sometimes if you have only powers of 5's only, that means in that place n will be 0. So only 5 powers will be existing. And if some numbers will have some numbers m and n, they will have contain both 2's and 5's together. So this is the way which we can express a terminating decimal. So this leads to us as theorem 1.5. Now let us state the theorem 1.5 now. Now the theorem 1.5 states that let x be a rational number whose decimal expansion terminates. Given x be a rational number, the decimal expansion is terminates. It is given that it terminates. Then x can be expressed in the form of p by q, rational number form, where p and q are co-prime. Co-prime means they don't have any common factor other than 1. That means they are in simplest form. P by q is in simplest form. And the prime factorization of q, that means the denominator. The prime factorization of the denominator is of the form 2 power n into 5 power m, where n and m are non-negative integers. N and m are non-negative integers. So you are given x as a rational number whose decimal expansion is a terminating decimal expansion, and then this x can be represented in the form of p by q, where p and q are in simplest form. That means p and q are co-prime, and this denominator q is expressed in the form of 2 power n into 5 power m, right? So this 2 power n, every denominator whose decimal expansion is terminating, the denominator will be always in the form of 2 power n into 5 power m. So what if the reverse, if you think in the reverse way, the converse of this theorem, that means the converse theorem states that what if it is true or not, you check. If the denominator is in the form of 2 power n into 5 power m, then is it always a decimal expansion which terminates? Yes. If the denominator is of the form 2 power n into 5 power m, then definitely p by q is a terminating decimal. So you have both ways you can understand. Theorem 1.5 says that if the denominator, if the p by q is in terminating decimal, then the denominator will be always in the form of 2 power n into 5 power m. Whereas in the reverse of the theorem 1.5, which is now theorem 1.6, let us go to the theorem 1.6. Let x is equal to p by q be a rational number such that the prime factorization q is of the form 2n into 5 power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. Observe this statement. If it is given now, if p by q is a rational number where the denominator has the prime factorization like 2 power n into 5 power m, then that decimal expansion definitely terminates. So this is the theorem 1.6. So theorem 1.6 is nothing but the converse to the theorem 1.5. So read carefully theorem 1.5 and theorem 1.6 statements. They are exactly converse to each other. So this theorem 1.6 is also true, which is a converse of theorem 1.5. So let us see some exercise questions in the next video.